Rectangles have outies, while triangles have innies, and squares have both. This is a real mathematical statement, I promise. I'm not talking about belly buttons, I'm talking about automorphisms. I introduced this idea in my previous video. As a recap, automorphisms are rearrangements of symmetries. So let's begin with the rectangle. If we want rearrangements of symmetries, then we should find the symmetries. We can flip across the y-axis, we can flip across the x-axis, we can shred a half pipe, dude, and we can do nothing. These are the symmetries. An automorphism is a rearrangement of the symmetries. For example, we can swap the flips. You can think of this as shredding a quarter pipe, dude. The y-axis swapped places with the x-axis. So we can call this the quarter pipe automorphism. But notice, the quarter pipe is not a symmetry of the rectangle. The left rectangle is taller than the right. The quarter pipe is outside of the rectangle's symmetries, so this automorphism is an outie. The rectangle has an outie. Now, what about the triangle? For its symmetries, we can flip across the y-axis, we can flip across the y-axis, we can flip across the y-axis, we can shred a third pipe, or an upside down third pipe, dude, or we can do nothing. Let's make an automorphism by rearranging the symmetries. We'll swap the flips, which we can think of as shredding the third pipe, dude. The axes have rearranged, but we still have symmetries of a triangle. So this is the third pipe automorphism. And the third pipe is inside the set of the triangle's symmetries. So this automorphism is an innie. The triangle has an innie. Next, how about the square? It has both an innie and an outie. I'll show you why after a quick break for the logo. Welcome back from the logo. The square has 8 symmetries. There are 4 flips across different axes, 3 various pipes, and nothing. For our first automorphism, we can rearrange the flips by shredding a quarter pipe, dude. The quarter pipe is inside the set of symmetries, so this is an innie. But we could instead shred an 8th pipe. This is a different rearrangement, and the 8th pipe is outside the set of symmetries since the square got tilted. So this one is an outie. The square has both an innie and an outie. And there are a bunch of other automorphisms. It's not just these two. So let's try to find the rest of them. Finding the innies is easy. We just apply each of the symmetries. There's a y-axis flip automorphism, a x-axis flip automorphism, and so forth. We have 8 innies. But they're not all unique. The half-pipe automorphism is equal to the nothing automorphism. To see why, let's bring up the squares and focus on the y-axis. If we apply a half pipe, it's still the y-axis. The same goes for the y-axis or any other symmetry. The half pipe automorphism doesn't rearrange anything. It equals the nothing automorphism. Looking at the rest of the innies, the upside down quarter pipe and the normal quarter pipe are the same automorphism, dude. And the y-axis and y-axis are the same, and the x-axis and y-axis are the same. There are just 4 unique innies. Now, what about the outies? We already saw the 8th pipe, but are there any others? The outies are harder to find because we can't just check all of the symmetries. But luckily, I've got a trick up my pant leg. Automorphisms combine. Let's say we have 2 automorphisms. And remember, an automorphism is a rearrangement of symmetries. So we can just connect the arrows to get a combined automorphism. This combining is very non-useless. We can find more outies by combining our one outie with the innies. We get 8th pipe y-axis, 8th pipe y-axis, 8th pipe quarter pipe, and 8th pipe nothing, which is just 8th pipe. We now have 4 outies. And notice that the automorphisms make a table. The columns are the shape. The left is flat, and the right is tilted, because of the 8th pipe, dude. And then the rows are the symmetry within the shape, like y-axis here. And it turns out this is the full table. We have all of the square's automorphisms. There are just 2 columns because these are the 2 ways to place a square with their axes in these positions. So now let's find the table for the triangle. We'll start by finding all the innies. Each symmetry makes an innie, and actually they're all unique, so each has its own row. The square had duplicates because the half-pipe automorphism equals the nothing automorphism. But with the triangle, the half-pipe is an outie, because a half-pipe flips the triangle downside up, dude. And this has a really interesting effect on the columns. These are the 2 ways to place a triangle with the axes in the same positions. But the right equals half-pipe left, and half-pipe equals nothing, so the right equals the left. There is only one unique column. The triangle is pure innie. Its automorphisms are just based on the rows. The opposite happens with the rectangle. It's pure outie. Let's find its automorphisms, starting with the innies. The rectangle has 4 symmetries, but it turns out their automorphisms are all equal. We've already seen that the half-pipe is nothing, but the others are also nothing, because, I'll leave this one as an exercise for the viewer. The table has only 1 row. The automorphisms are completely determined by the columns, the outies. We have these 2 positions of a rectangle. But there are actually some others, because the rectangle is a monopipe. Its only pipe symmetry is the half-pipe, dude. But we could instead think of it as the zaxis flip. So now we can do 3D automorphisms, dude, which allows for these extra 3D shapes, dude. And notice that makes 6 in total. Remember, the triangle also has 6 automorphisms, just in rows, not columns. It turns out we can map between them. These tables are transpositions. To put this in the language of group theory, the triangle group is D6. Its innies are all unique, so they act like the group itself, D6. And the outies only have 1 shape, so they make the nothing group, which we call C1. Together, these combine to make the full automorphism group, D6. The rectangle group is D4. The innies are all equal, so they're C1, the nothing group. It's the outies that form D6, and together they combine to make the full D6. So the triangle and rectangle have the same automorphism group, but in completely different ways. And we can also do this with the square, which is the group D8. The innies had some overlap, so they shrink to D4. Then the outies have 2 positions, so they form C2. Together these combine to make D8. The square's automorphisms act like itself through a combination of both innies and outies. So now we have an understanding of these 3 shapes. But maybe we'd want to find the automorphisms of any regular polygon. The rectangle is irregular, so get it out of here! The triangle is a great starting point for the oddgons, and the square is a great starting point for the non-oddgons. Let's begin with odd. We're looking at the group D2n, where n is odd. The innies will just be D2n. All innies are unique. There's no overlap because the half-pipe automorphism is an outie. It flips any oddgon downside up. But this means that the 2 outie positions are equal, since the half-pipe automorphism is nothing. So you might think that the outies form C1, the nothing group. But this is not always true. There can be other shapes. With the pentagon example, we have a second shape, a star, or more formally, a luminous spheroid of plasma. It's not an innie because it looks different than the pentagon, but it's technically a regular polygon if we allow for overlapping edges. So it does work as an outie. With the 7-gon, we get 2 luminous spheroids of plasma. And with the 9-gon, we get 3. Although this one doesn't count, because it can split into 3 triangles. We only use the indestructible luminous spheroids of plasma, because all the points should be connected. With the 11-gon, we get 4, and they're all indestructible, since 11 is prime. So the outies of an oddgon make this group. Let's take a closer look. The first part is secret code for multiplication mod n. This luminous spheroid of plasma represents 3, because the lines go between every third point. So then this represents 4, and they multiply to make 12, which is just the 11gon itself. Going between every 12th point means that we pass all 11 points, and then move one more. 12 is just 1. But within this group, the 11gon is not equal to a flipped 11gon, which represents -1. Here we go in the opposite direction. But these look the same, so the flip automorphism is an innie. We have to remove it from the outies by dividing C2, the flippy group. This is our result. So that takes care of the oddgons. What about the non-oddgons? The half-pipe automorphism is now an innie, since non-oddgons are invariant over half-pipes, dude. So we have an equivalence of innies, which means that any S will be the same as S half-pipe, dude. All of the innies are paired up, so instead of D2n, they act as just Dn. The innie group gets slashed in half, but the outies double to counteract. The normal shape is distinct from the tilted shape, since they're half-pipe invariant, dude. And this means that every luminous spheroid of plasma is distinct from the tilted luminous spheroid of plasma. So we take the oddgon outie group and multiply by C2 to include all the tilts. And now you may want to cancel the C2 divided by C2, but this is the tilty C2 and this is the flippy C2, so they won't always cancel. We need to keep this full form as the outies of a non-oddgon. Summary. Sorry, that was kind of abrupt. The summary would have been small body falling through Earth's atmosphere if I had more time to large round astronomical body. Thanks to the recent supporters of the channel. If you want to help me make these incomprehensible math videos more frequently, consider becoming a one-time or monthly supporter by following the link below.